Hey everybody, today we're doing more hypothesis testing. In particular, we're considering a situation where we have two populations and we'd like to know whether the proportion of successes in each population is the same or different. For instance, we might want to know, are men more likely to own dogs than women? Or are people over the age of 45 more likely to attend religious services? This means we're examining a specific sort of null hypothesis in our significance tests. H naught is going to be P1 equals P2. The population proportions are the same. As usual, we're going to test a null hypothesis like that by gathering sample data. We're going to get P1 hat and P2 hat, population, or rather the proportion of successes in each of two samples from each of the two populations. We're going to look at the difference. We're going to say how likely or unlikely is the P1 hat minus P2 hat that we got through random chance, assuming that P1 and P2 are the same, that the population proportions are the same. By the way, notice that P1 equals P2 is the same thing as saying P1 minus P2 equals 0. So that's kind of where the P1 hat minus P2 hat is coming from. So to answer this, we have to think in terms of the entire distribution of P1 hat minus P2 hat. So you imagine going out and getting a sample from each of these two populations and getting the P1 hat minus P2 hat, getting some number for that, then doing it again and again and again and again, doing all the possible samples from these two populations. What kind of distribution does P1 hat minus P2 hat have? And, in particular, where does our P1 hat minus P2 hat fall in that distribution? Is it a very unlikely result, or is it pretty mundane? So I said we need to consider the distribution of P1 hat minus P2 hat. We can construct that pretty quickly because we know that each of the P hats are going to be approximately normally distributed, assuming a reasonable sample size. In particular, we saw in the last videos that each of the PI hats, has a normal distribution with mean PI and variance PI times 1 minus PI over NI. Here, Ni is the sample size from the ith population, first or second. Next, we need a little bit of old knowledge about linear combinations of random variables. The expected value of a difference in random variables is the difference in the expected values, and the variance of a difference in random variables is the sum of the individual variances. So using that knowledge, we can write the distribution of P1 hat minus P2 hat. We know it's going to be normal. The sum or difference of random variables the sum or difference of normal random variables is again normal. The mean is going to be P1 minus P2, and the variance is going to be P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. So in the context of a significance test, we're estimating P1 with P1 hat and P2 with P2 hat. It means that we can use this z statistic to do our inference. As always, we compute a z statistic by doing the statistic we got minus the expected value over the standard deviation of the statistic. Now, in this case, the null hypothesis is that P1 equals P2, so the expected value is just 0. So really, all we're getting for z is the statistic we got, P1 hat minus P2 hat, over its standard deviation, that big square root in the bottom. Let's do an example. A high school offers two sections of trigonometry, one at 8 a.m. and another at 1 p.m. Last year, the 8 a.m. class had 25 of 32 students pass, while the 1 p.m. class had 18 of 30 students pass. Is there sufficient evidence to believe that the failure rate in the two sections is different? So obviously these two proportions, 25 out of 32 and 18 out of 30, are not identical. They're different. So on the face of it, it does look like there is a different pass-fail rate in each of these two classes. However, that could just be due to random chance, and we need to know how likely is it to get data like this due to random chance if, in fact, the probability of passing each class is the same. We're going to test at alpha equals 0.10, so when we get a p-value at the end, we'll compare it to this. And if p is less than that alpha, we'll reject a null hypothesis and conclude that, in fact, the chance of passing each of the classes is the same. So So let's start with hypotheses. We're interested in testing whether the proportion of students that pass each class is the same. And again, I'm talking about the population proportion, not just these individual classes, but just in general, all the 8 a.m. classes, 8 a.m. trigonometry classes that they could have, and all of the 1 p.m. trigonometry classes that they could have. H naught is going to be the idea that our sample data is just due to random chance, that in fact the pass rate in both these classes is the same. The alternative hypothesis is the opposite, that it's not. Here, I've chosen a two-sided hypothesis because I don't want to make any assumptions about which class might be harder to pass. And in general, we know that's our default option. If we don't have a strong reason to suppose a one-sided alternative, we default to a two-sided. Now we compute a z-score for our sample data. Basically, I'm just plugging into that formula that I got a minute ago. I'm using P1 hat is 25 out of 32, 0.781 approximately, and P2 hat is 18 out of 30, so 0.60. I plug in and do a little arithmetic, and I get z is 1.57. Now this is a two-sided test, so I need the probability of getting a z-score at least that extreme in either direction, so bigger than 1.57 or less than negative 1.57. And again, of course, I'm talking about the z-score in the context of the standard normal distribution. So I compute that using a normal CDF. Normal CDFs are talking about the probability of getting a z-score less than something. So I'm going to take the probability that z comes out to be less than or equal to negative 1.57 just by random chance. And I'm going to double that to get the less than and the greater than. The less than negative 1.57 and the greater than 1.57. Overall, I get 0.116. So that's a p-value. That's saying that if the null hypothesis is true, we would get data at least as extreme as what we got by random chance about 12% of the time. So that's not a tiny percentage. In particular, it's bigger than the threshold that we set, alpha equals 0.10. We said we were going to only reject the null hypothesis if we got a p-value less than 10%. We didn't, so we cannot reject the null hypothesis in this case. There is insufficient evidence to conclude that the failure rate in each of these two classes is different.